Hello, everyone. Um, Welcome to this very simple code walkthrough where we will learn to build a simple movie recommender system using just embeddings. So, the key concept that we will really try to hammer down in this walkthrough is what is an embedding and how can we leverage them to make useful stuff. So there are some prerequisites for the walkthrough that you should have already set up before beginning. The first one is to set up a Python virtual environment using PyEnv or VEnv. I usually use PyEnv, is what I recommend. I really like it. You must have a Kaggle account and a Hugging Face account. And don't worry, both of those things are free and you will find them very useful, I'm sure. So the first thing we need to do is to download the data sets we're going to work with. And remember, this is just, we're not building a production system. So we're going to use some very simple data sets just to illustrate the concept that we want to, really understand. So what we're going to do is we're going to use this data set from that you can find on Kaggle. And it has basically two files that you should download: the TMDB 5000 credits and the TMDB 5000 movies. Just two CSV, nothing big. And this data set has been used in countless of examples. So we're gonna just leverage here also. So go ahead and download that. Of course, I have already downloaded it. And then we're just gonna install some requirements. Now, I've already installed all of this in my virtual environment, so it might take a little some time for you. And you notice that the first thing I do is I'm installing UV, which is it's basically a replacement for pip, the Python package manager. And that replacement, the reason why I use it is because it's a lot faster. So if you ever try it, you will notice that it is the same as far as I can tell in my tests, but it's just a lot faster. So I always use that UV. Um, so we're gonna go ahead and install some packages, and we're gonna go right in, and we're gonna start importing some libraries. I don't know, like what we're gonna use by heart. I don't know every single library. So I'm just gonna import a few things, and of course, if we need something else in the future, we're just gonna, import that. The first thing we want to do is explore the data frames that we have just downloaded, or that you should have downloaded. So TMBD 5000 movies, and we're gonna go ahead and create this data frame, and we're gonna do TMDB 5000 credits. Load them both in, and I find the easiest way to just get a quick glimpse into a data frame and what it's about is just to look at one of the rows. Obviously, this is not comprehensive data analysis or anything, but I just want to look at what the rows contain. So we see that the movie data frame has a bunch of columns, including the budget for the movie, the genres for a movie. It seems like one movie can have different genres. That makes sense. There are a bunch of keywords, the overview, which is like what the movie is about, I guess. Release date, a bunch of stuff. The tagline, Enter the World Pandora, and of course the title, which is Avatar. There's a lot to work with here. And we also have then the credits data frame, right? The first column we have, sorry, the first row we have four columns, right? The movie ID, the title, the cast, and the crew. We can see that there are many, there can be, of course, the cast is a list and the crew is a list. Let's explore a little bit more about that. So let's see how the crew is. Okay, it's a bunch of stuff. The editor, production design. So it's just a bunch of, it's a dictionary, right? Each entry is a dictionary with a bunch of stuff about the crew. And I'm assuming the cast is very, very similar. Sam Worthington, Suzaldana, yada, yada, yada. Right. So we can work with this. And what we're going to do is we're going to try to use the information here to build um, like some sort of representation of a movie. Like what information in both of these data frames is useful to represent a movie. So the first thing we might want to do is just put them all together into one data set. It's just easier, and conveniently we have this ID here, movie ID and ID, that we can join both data frames on. So the first thing I'm going to do is going to rename the credits data frame. I'm going to rename movie ID. I'm going to rename that to ID. This is how you do it. You can do it's true. Right, and now once that is done, we can join both of them, right? So we can just merge both data frame on the just on the ID. And wait, let's see, why did that not work? Oh, right. Sorry, we gotta do that. There we go. Okay. Sorry about that. Okay, so now we got one data frame, and you notice that I expect this to generate some new columns like title Y and title X. Like if both data frames have the same column name, it will create this suffixes. So yeah, we don't need that. We're just gonna keep original title, I think. So what we're gonna do is we're gonna first drop the columns, the title X, and title Y. If I remember correctly, drop takes a list. Do X is 1, and we can do in place equals true. So those should be gone. Yeah, and now we can just do here the rename, and we're gonna rename the columns original title. This is just for convenience. We're gonna use title quite a lot, so might as well just rename it. Original title should be a dictionary. Original title, we're gonna rename that to title. That's just for my peace of mind. True. Of course, you can feel free to modify and adapt all of this. I always like to think of the code behind an idea as just a detail. It's a rather important detail, of course, otherwise the idea doesn't do anything. But the important thing is to understand the concepts and the ideas um, behind what makes a system work rather than just the code itself. All right, so now that we have just one data frame to work with, what we're gonna do is we're gonna try to convert, create this representation of a string. And for this, I am going to cheat a little bit, and just because I don't want to spend too much time on that. And I'm gonna copy some code that I have um, already written, sorry, to parse some of the columns in the data frame. You can see that some of them are like, they're like JSON formats, and I don't want that. So what we should do is we should just parse them to build a representation of what a movie is, what's important in a movie that might, make you want to watch it or not, or make you not like it. And so what we're gonna do is we're gonna set up these auxiliary functions here, where the first one is just gonna take the name, uh, the name element on the list, and we're gonna use that for the um, the the um, the genres and the keywords. So if you see here, each keyword has a name, like call to clash that tells you, you know, some keywords about the movie, and the same thing with the genres, right? You got action, fantasy, whatever. So we're gonna use that function to just get all of the keywords for a movie and all of the genres. This function we just wanted to get the director of the movie, which is important. Remember that we had this cast JSON object that it potentially reflects the entire, you know, casting. The crew, the entire crew. We had the crew, which potentially the director is in there. And then we have these other functions called get top cast that, you know, it's also important, like in a movie, who's leading it, right? Who's starring it. And what we're gonna do is we're gonna take the top three first cast members that we get. Um, and then of course we're gonna get the overview, we're gonna get the tagline of the movie, and what we're gonna do is actually okay, let's run this actually. Okay, right. Oh, right. So JSON is undefined. So we're gonna import JSON. We're gonna just import libraries as we go along. And what we're gonna do is we're gonna create a new column called soup. It's called soup because, you know, it's like a soup of stuff that describes a movie. You can see here that the soup is just the overview of the movie, the genres, the keywords, the tagline, the cast, and the director. So in the 22nd century, a paraplegic marine is dispatched, blah 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 blah. And then we got the keywords. Sorry, no. Then we got the genres, and then we got the keywords, and then we got the tagline. This one enter the work, and then we got the actors, and lastly the director. So you can see that there's not a lot of structure here. It's just, you know, just the text. Actually, we might as well. Actually, I think we should get the title in there, right? Title seems important. Let's put the title. Okay, avatar. Yeah. Okay, great. So this soup, what I call soup here, is what we are going to use to represent a movie. And I think that you can add more stuff here. Like I said, there are many columns that you could potentially add to the soup, right? And that, you know, there's some information that I left out that might be useful. That's up to you. But this is the idea, right? We want a string that represents all of the relevant information that determines, you know, if you're gonna like a movie or not. Basically, that's the idea. And now we just need a way to, you know, measure how similar to these two strings are, right? So if I, you know, if I look at the second movie, right, Pirates of the Caribbean, like how similar is Avatar to Pirates of the Caribbean at World's End, right? We need a way to measure this, and what we're going to do is we're going to use something that is, well, it's we need to embed, and this is where the embeddings come in. We need to embed these two strings into a representation that we can numerically, you know, measure. And the idea is that we can turn these two strings into vectors, and then using just vector math, we can determine how close, how similar, not how close, how similar two vectors are. And I'm gonna try to illustrate what I mean here. So I'm gonna go ahead and pull out a whiteboard, and bear with me. But the idea is that, let's say you have this plane here, right? It's just a two-dimensional plane, right? We got y and we got x, and we manage to somehow, right? Don't worry about how for now. We'll go into that later. we managed to somehow turn each movie into a vector that we can plot in this space. So let's say we manage to turn Avatar into a vector that's 1, 1. And this is Avatar. Like, this is the representation of the movie Avatar in this space. So what we could measure is how similar is another movie to Avatar using that movie's representation. So let's say we managed to do the same with Pirates of the Caribbean. And we can see that Pirates of the Caribbean falls right around here, which I'm going to say it's like, you know, 0.5 and then 3. So what we're going to use is something called cosine similarity to measure how how similar these two vectors are. In cosine similarity, the length of the vector, like this, the magnitude, like this length, doesn't matter. Like, it doesn't matter how long the vector is, right? All that matters is how is the angle to determine how similar these two vectors are. And we can see that they're both kind of pointing in the same direction. And so we can say that these two movies are similar. So let's say we had another movie, right? That gets, we represent it in a vector and it lands here, -1, -1. The, you know, um, the cosine similarity between these two movies, Avatar and this new one, is going to be -1 because the vectors are pointing in completely opposite directions, right? And the cosine similarity between these two might be positive, like it's going to be positive, right? Because they're pointing in the same direction. And if you get vectors that are completely orthogonal, like this, then this is -1, 1. We are going to get a cosine similarity of 0, right? Because this angle is like 90 degrees. So we're going to get a cosine similarity of 0. And, these two movies, is not that they're complete opposites, it's just that they're not very similar, right? Whereas these movies, these two here are similar. And that's the idea behind cosine similarity. You can go ahead, and I actually do encourage you to look more into this, like more into the actual formula that I just described. But it's not essential for this type of for this walkthrough. The actual math is not essential. The important thing is that you understand the concept that vectors that are pointing in similar directions are going to have a higher cosine similarities than vectors that are pointing in opposite directions or very different directions. And that's the idea. So now we have to do it. The first thing we need to do is find a way to turn these strings into vectors. And for that, we're going to use something called sentence transformers. And this is where you might actually need access to Hugging Face. And so I don't remember the name of the model, so I'm just going to put it here. But we're going to import library from sentence transformers, import sentence transformer. There we go, transformer. Oops. And we're going to use this model. And this is, you can go ahead and look up the documentation of sentence transformers. Is based on Hugging Face. I think it's great. You might need a Hugging Face account for this. You will need to set that up. But yeah, and what this is going to do is we can actually encode each string, right? Each movie using this sentence transformer model. And we can just go ahead and say movies, and let's soup. So we're going to take all of the soup, we're going to put that into a list, and then we are going to do let's see, movies encoding Esbern model dot encode, and we can pass the movies to it. So it takes a list of strings. We're going to get a bunch of encodings. Actually, let's kind of call it Embeddings. should take a little bit of time. Let's do it again. But it should be pretty fast because it's a small model. So we're gonna go ahead and do that. And now what we can do is we could actually, you know, use this embedding to, we get a new movie, right? Or a new whatever, any string really, and we find how close is to all of the ones that we just embedded. I hope that makes sense. Um, we can see that we have 4,803 movies, and each vector that represents a movie is 384 dimensions. So in the example we saw, there's only 2 dimensions, just because it's easier to draw. But these vectors actually have 384 dimensions, which we obviously cannot draw, and it wouldn't make a lot of sense. Um, but that's the representation. And cosine similarity works no matter, if you have 300 dimension or 2, right? It doesn't matter. It will still work. And we can let's go ahead and try it, right? So we could have a movie that's, let's say I want to watch, a Western, right? So I'm just gonna go ahead and query that, and then I'm gonna go ahead and get the query embedding. I'm gonna go, notice that it's the same process, right, for the query than for the movie that we already have. Obviously, we gotta, take the string, put it into the same embedding space, and then compare them. That should work. And we now have the query embedding, which is, it's one embedding of 384. And all we have to do is compare this one embedding to this other 4,803 embeddings. And we need, we're going to use cosine similarity. So we're going to import that. So from sklearn dot pairwise, I don't remember the import symbol. Let me find that real quick. Yeah, metrics. Okay, sklearn dot metrics, the pairwise import cosine similarity. There we go. And what we're going to do is we are going to simply take the cosine similarity, and we're going to take the query cosine similarity between the query embedding and the SBIRD embeddings. See what we get. We should also get, a set of vectors, basically. Yeah, so we have 4,883 cosine similarity values. And what we're going to do is we're going to find, the highest one. What's the highest similarity? And for that, we can do, so let's see, we want the top K. We're going to sort them. And we're going to find the highest one. So we're going to do top K. And here we have the indexes that, in our data frame represent the highest similarity movies to the query Western. And notice that Western is not necessarily the name of a movie, I don't think. But since we embedded the entire soup, hopefully there will be something closer that that has Western in it, right? That soup, like the genre might be Western, the overview might say something about Western movies, so on and so forth. So let's actually take a look at what are those movies. Okay. Let's actually get the top 3. I just noticed that I named it top K, but I didn't do any K. All right, so let's get the top 3 here. Okay, and let's just do here top 3. Title, right? So instead of getting the whole thing, let's just get the title. Okay, so Western Religion is the first one, Slow West, and then The Ridiculous Six. I know that The Ridiculous Six is a Western movie. Um, so I guess it works, right? It works to an extent. This query is a simple query. Of course, like we could do, Avatar, right? And do that. And we should get, Avatar, right? Avatar, The Last Airbender, which is also Avatar. It's just a different Avatar. Um, but it seems like it works to an extent. And I mentioned earlier that we are looking at, we're doing this by finding movies that, or actually, soups. Let's call them soups because it's a representation of the movie, right? We're finding these strings that are closer to the query, and closer, it can be a relative term, but what I mean here is that it's closer semantically. So the measurement of closer depends on how this sentence transformer was trained. Now, I don't know how this particular transformer was trained, but what transformers do when trained with text is that they gain a semantic understanding of the text that they intake, and so we can leverage that semantic understanding to measure how close two strings are semantically speaking. So if you can think of two words, like before we had sentence transformers or, LLMs, obviously, we used to do this with words, and we would find words that are semantically close, right? And we would train models to produce a vector representation based on the semanticity of these words. So you can think of the word king, that it would have its own vector, and then queen is going to have its own vector. It's not going to be super close, right? But it's going to be close to kin because they're both monarchs, and so they're very related semantically. Of course, the problem, and I'm sure some of you can already visualize the problem with this, is that once you have a word that can have very different meanings depending on the context, this is of course going to fall short. This type of word embedding is the way they are called. It's going to fall short because if you think of the word bank, it could be a river bank or an actual bank, like the entity. And so just word embeddings are not enough when it comes to complex, when you try to capture complex semantic relationships, right? And so that's why word embeddings are no longer used now that we have these powerful systems that can actually intake entire sentences and give you a representation of where that sentence lands semantically in this multidimensional space. Yeah, I hope that makes sense. But it seems like it works. Ideally, what I like to do is to get some sort of, a little bit of a visualization into, where, how does this space looks? Obviously, we cannot even imagine a 384 dimensional space, right? That's very hard. It's out of the question. But what we can do is we can try to shrink that space while keeping most of the information and try to visualize, where these movies land in that space and see if we can get, a nice visualization um, out of it. And for this, I'm gonna cheat once again because this is a lot of code that I really don't want to, I don't want to waste your time. Write it down. I'll go over it very briefly, um, but it's not super important. We gotta import pagmap, and don't worry, I'll explain. I'll explain everything. Let me just put that in there. Okay, so what we're gonna do is we're gonna use a technique called dimensionality reduction, and there are many methods to do this. I prefer this one. I like this one. PacMap. But what we're essentially doing is, since we cannot visualize a 384 dimensional space, that wouldn't make sense. We're just gonna reduce it into two, while keeping most of the information. Obviously, all of the visualizations that we're gonna see here are now, you know, an approximation, right? They're gonna be noisy visualizations, but I think it still looks quite cool and gives you a more visual understanding of what's happening. And so here, what we did is, like I mentioned, we took the embeddings, we reduced them into 2 dimensions, and you can see here one dimension, there's the other one, and then we visualize them using Plotly, and we can see here that the different type of genres where they land. Of course, this is again a bit misleading because one movie has many different genres. I just took the first one for this, um, which I'm assuming is the predominant one. But we can see that, for example, let's take a look at what this cluster is here. We can see that it's all Star Trek, right? We have like a little, part that outside the main blob that is just Star Trek, which is interesting. We can see here that all of the superhero stuff is around here. The Avengers, Green Lantern, Captain America, X-Men, Doctor, don't know what that is, MacGruber. Superhero stuff is around here, and it's quite interesting to see that. Of course, it's a hard task for this embedding model to actually separate everything so perfectly because movies are complex, right? Like I mentioned, they don't all have one genre. And movies that have different genres can be similar in overview. But we can see that I have a sense that we are creating, interesting, like meaningful cluster, right? Apparently this cluster is all about Christmas, and yeah, it's just useful to look at. Now, I wonder, you would notice that this this query is a very simple one, right? And I'm wondering how far we can push this. And actually, let's put this into a function, right? Let's def get okay. Let's put this into a function just just um, uh, just so that we can reuse it easily. Let's put that there. Put that there, and take the cosine similarity and return the top k, return top k, and we're actually going to add an additional parameter here. Be optional. It's going to top k. I'm going to set it to 3. All right. So let's put that into a function, make it easier for us to reuse. And what happens if we try top k alpha and then sperm. Yeah, okay, still works. What happens if we try a more complex query, right? What happens if we just get, let's see. Okay, good. What happens if we try, like a really complex query instead of just saying, "Oh, give me movies similar to Avatar," and what I would like to try is a query that is something like this, right? Let's see. Top K, get top K. Let's put this in there. And a query that is more complex. I'm gonna copy and paste this. Something like this, right? Visually stunning science fiction movie with a strong female lead. And let's see what we get. How does our simple model fare against such a query? So I don't know all of these movies, right? But I do know Bathing Beauty, right? If I remember correctly, Bathing Beauty is like a movie from the 40s, so it cannot be visually stunning. Let's actually do okay equals 5. The Boy Next Door doesn't sound like a science fiction movie, so we can see that there are some limitations to this, and of course, the limitations come from the very core principle that this embedding model is a small one, right? So, it might not be powerful enough to capture very complex semantic information, right? Like visually stunning science fiction movies with strong family. It's quite a lot for a small model to capture. And so, a simple, you know, thing we can try, and notice that this already works to an extent, but we're just trying to extend it a little bit, is to use a more powerful embedding model. And for this, I'm going to cheat once again, and I'm going to use the OpenAI API to embed all of our sentences, sorry, all of our soups, um, into basically the same process, right? Meaningful representation, get the cosine similarity, everything is going to be the same, but instead of using a sentence transformer, we're going to use an OpenAI embedding model through the API. This part is optional, as of course it is not free. You will have to pay some API costs, although it's rather cheap. Um, but yeah, let's see if we can actually get something meaningful back when we input this query using a stronger uh, embedding model. Just some imports. Don't worry too much about this. This is the name of the model that we're gonna use. I like to use Light LLM. I really recommend it. Check it out for all your LLM API needs. Love Light LLM. We're just gonna batch everything here. Um, we're just gonna embed everything, right? Remember, it's the same process, right? We're taking each soup and we're just gonna get a vector back. That's it. That's all we're gonna do, and I'm gonna show you how that looks. But the process is exactly the same. Like I don't want you to be worrying about the code or confused or anything like that. The process is exactly the same. This is all just boilerplate so that we can use the OpenAI API. But it is exactly the same procedure, and we can see, oh, it's actually right there. We can see that we get the same amount of embeddings, obviously, because we have 4,903 movies, and we get 1,536 36 dimensions. So it's a higher dimensionality, and let's see how that goes. But first, let's visualize it. Right? Let's see how different the projection looks. Right? Let's take a look at that. Let's take a look at that. And we need to replace this with embeddings. Hopefully this works. Yeah, we can see that the shape of the embeddings is, well, obviously remember this is an approximation, right? It's quite different. And I really like that, the colors are more grouped from where I can gather with a quick inspection. So I already like quite this. Sorry, I already quite like this more than what we had before. So let's go ahead and let's give it a shot. So unfortunately we cannot reuse the same function because I believe the method, yeah, it's not the same. So we're just gonna go ahead and use this. Quite simple. Just gonna So the input is going to be the query, and the um, the embedding, query embedding, I think comes from response embedding. Let's take a look. Our response data. Okay. Response data. And then embedding. Yeah. And then we can reuse this very simple line. Where is it? Yeah. We can just reuse this to get our top K. Here we go. And I'm just gonna put, top K 3 as usual. And let's see how this works out. Should run, maybe not. Yeah. So of course, first thing is that they should not be Spurt embeddings. It should be OpenAI embeddings. But I also think that they should have an extra dimension at first, and that's why it's complaining. Yeah. Sorry. There we go. And we're gonna get the top K. We already have the top K. Let's print and see if this is any better. Remember, before we got Bathing Beauty, Heavy Metal, The In Crowd, The Boy Next Door. And here, this is a lot better, right? We got Lucy, Jupiter Ascending, Ion Flux. I definitely know that Lucy is a science fiction movie with a strong female lead. And I also think Jupiter Ascending has a female lead. Aeon Flux also has a female lead, as far as I know. And they're all science fiction. So we can see that by simply using a more powerful embedding model, it actually makes a very stark difference. Now, you might notice that this is not a recommender system strictly. A recommender system usually has a representation of what a user likes. Of course, there are many ways of doing this, and we're going to use a very simple approach, which is we are based on what a user likes and doesn't like. We're going to build a vector that represents the user in this same space, right? So the user might land here. The representation of the user might land. Let's say we have this space. Based on what the user liked. The representation of the user might land somewhere here, and we know we can recommend this type of movies. Right? Of course, like I mentioned, this is very simple, right? And usually, recommender system is going to have, what Netflix recommender system has a lot more stuff added on top of that. But this is just to show what can be done, right? To explain the concept that well, to illustrate the concept that I just mentioned, I'm gonna just copy and paste this example that I already have drafted, and let's go through it. So let's just say that we have, we can represent a movie with just two dimensions, right? And the first dimension means, how dramatic the movie is, or how horror the movie is, how scary, I guess. How close to the horror genre is. So we have two dimensions. The higher the first number goes, the more dramatic the movie is, and the lower the number goes, the more horror-like the movie is. And we can build a user profile by saying, oh, this user watched a movie called Movie Drama. That's a very, very clever name. And it gave it a five star rating. And it then watched another movie called Movie Horror, which he hated, and it gave it a 1-star rating. And so what we can do is say, oh, okay, well, we can take the embeddings of those movies, right? The movie drama 9-1 and movie horror, and push them up or down based on how liked they were. Let's run this. So what I mean is say, okay, the movie drama gave it a 5, so we set up a baseline that is 3. Say, the rating is 3, so the user did not like or dislike this movie, right? This is, of course, a decision I made, but of course, you can play around with this and make, devise much more clever methods, right? But for simplicity's sake, I just said, okay, if the user gave it a 3, he neither liked it nor disliked it. And so we're going to ignore that. Anything above 3 or below 3 is going to move the vector of said movie. So, and this is what's happening here. You gave it a 5, so the difference, how high above 3 is it? That's 2. We can see that the embedding for the drama movie, which was originally 9-1, gets shifted into 18-2. And we can see that for horror, the same thing happens, but instead of 2, it's minus 2. So this vector gets shifted to -4, -2. So they get moved around, right? And then we calculate the weighted sum um, of these two vectors, right? And normalize them, and we get this profile embedding. So the ideal movie for this user is going to be drama. So because the user likes drama. So we can see that. Remember, the value of the number is not so important because we're using cosine similarity. What's important is that the direction of the vector. So you can see that this is positive, right? This first value here is positive, meaning that we like this value to be high. So drama movies. If I were to simply switch this around and say, okay, now we have another user that hated the movie drama and loved the movie horror, we can see that this will go down, right? Let's say that he didn't completely hate it; he liked it a little bit. It goes up, it goes up a little bit, right? Let's say he didn't think much of anything, then you'll only have the horror to guide you to recommend something. And I hope that that made sense. But basically, the concept that needs to remain there is that we are trying to place the user profile in somewhere in this space. We're trying to place it somewhere here based on what he liked and didn't like. Great. So now we're gonna apply the logic that we have in this example to our actual embeddings. So what we need is we need to have a way of extracting the embedding for each title. So we can create some sort of, let's say, title map, and what we're gonna do is for each title. So and the titles are in df process dot title dot the list. So for each item there, we're gonna put and the index for title and enumerate. It's probably a better way of doing this. Doesn't matter. Oops. So we're gonna get a title map, which is just gonna be okay so each title, where's the position in our array, so that we can then map them to the embedding. Then we need a set of user ratings. So which movie, which movies the user rated high or low. So we're gonna do I don't know. Let's find some movies here. So let's say that the user really liked Titanic, give it a 5. Oops. Really liked King Kong, give it a 5 as well. Did not like Iron Man. Iron Man hated it. He didn't like, so he doesn't like, let's say he doesn't like superhero movies. Avengers, Age of Ultron. Okay, let's put those at 1. And we have, so the user has watched these 4 movies, and that's the rating he has given. And so what we need to do now is something very similar to this, right? We are gonna create a dummy profile embedding that we can start filling out. What was so it's going to be OpenAI embeddings. OpenAI embeddings dot shape of 1. And once we have that, we can actually just apply this very same logic here. And for each title and rating, we're gonna have to change it a little bit. We can go into the title map, get the index, and get the OpenAI embeddings index times the difference. We compute the weight, and we divide everything at the end. So obviously now of course, each movie that the user has rated must be present in our database. Otherwise, this won't work, right? We gotta do dot lower here. Titanic dot lower. And there we go. So if this worked, we can look at the profile embedding of the user. It's the same shape as the OpenAI embeddings, obviously. And that's going to be a representation, hopefully, if this is all correct, of what the user likes. And what we can do now is simply follow the same procedure as we did before to find the closest movies to this profile embedding. So we can actually just reuse this part here. We can actually just reuse that part and see what we get, right? So instead of instead of the query embedding, we just want the profile embedding. And top K, obviously, top 3. And we can see that the movies that we can recommend to the user are Titanic, King Kong, and something else. Of course, let's shift this to top 10 because Titanic and King Kong, the user has already seen them. We would obviously need to edit this. This is just a simple example, but we would probably need to edit this to make sure that movies that we have already seen are excluded from the results, obviously. So and again, like if we switch this around and say the user hated Titanic, right? And we repeat the whole process again, we're gonna see recommended, all superhero movies. Okay, well, there you have it. We've built in just under an hour a very, very simple recommender system using just embeddings. And what I would really like, if you can take something away from this walkthrough, if anything, is just how the very simple idea of turning semantic knowledge into a representable, measurable space can have very, very powerful use cases. So thank you for watching, and I hope you learned something. I'll see you on the next one.